Most people assume electricity requires industry, but that assumption overlooks a quieter reality. Living systems have been generating usable electrical charge long before human engineering refined it. Beneath the surface of ordinary soil, at the boundary between plant roots and microbial life, electrons move continuously as part of metabolism. With the right arrangement of electrodes, that movement can be captured and directed through a circuit. A plant in a pot can power an LED continuously, not as a novelty, not as a temporary trick, but as a sustained system. The significance of this is not the brightness of the LED. It's the realization that, energy production doesn't have to depend on combustion, rotation, or stored charge. It can actually be embedded within a living ecosystem. And once you understand that, it really reframes how we think about survival, logistics, and resilience in environments where conventional infrastructure just can't be relied upon. To understand why this matters, we honestly need to begin with the biology. Now, the electricity, interestingly enough, comes from the soil ecosystem rather than from the plant alone. The mechanism behind plant-generated electricity is actually known as a plant microbial fuel cell. The plant itself, well, it's not acting as a battery. Instead, it's feeding a complex biological community that, in fact, performs the actual electrical work. Through photosynthesis, the plant converts sunlight into chemical energy in the form of sugars. Not all of it is used directly for growth. Some leaks into the surrounding soil where microbes consume it. In ordinary conditions, those electrons participate in chemical reactions within the soil. But if an electrode is placed in the oxygen-poor region near the roots, and another electrode is positioned in a more oxygen-rich environment, a potential difference forms. This principle builds on foundational electrochemistry explored centuries ago by figures such as Alessandro Volta, who demonstrated that chemical reactions could generate electrical potential. What modern research added was the understanding that certain microbes are capable of transferring electrons externally, effectively turning soil into a continuous bioelectrical system. As long as photosynthesis continues, microbes receive nutrients. As long as microbes metabolize, electrons are released. The process is regenerative and self-sustaining. Military planners became interested when they began confronting the limits of portable power. Throughout the 20th century, electricity became central to military operations. Radios, sensors, navigation tools, surveillance equipment, and later digital systems all depended on portable power. Batteries improved, but they remained finite. Generators provided higher output, but required fuel. Solar panels reduced logistical strain, but depended on exposure and storage capacity. Long-duration deployments exposed a persistent problem. Energy supply chains are vulnerable. During extended operations in remote environments, jungles, wetlands, mountainous terrain, resupplying batteries or fuel introduced risk. Equipment designed for monitoring or intelligence gathering sometimes failed not because of mechanical damage, but because its power source was exhausted. Research agencies began examining unconventional energy systems capable of operating independently of resupply. Among them was the Defense Advanced Research Projects Agency, which explored low-power, long-duration technologies for remote sensing. The appeal of plant microbial fuel cells in this context was not high output. It was persistence. A wetland plant growing undisturbed could feed microbial communities indefinitely. A sensor drawing only milliwatts of power could operate continuously without maintenance. This represented a different kind of energy logic. Instead of transporting power into an environment, the environment itself produced it. History repeatedly shows that systems which regenerate outperform those that merely deplete. Across multiple 20th century conflicts, logistical failure often determined outcomes more than battlefield tactics. Armies with superior equipment sometimes faltered when supply lines stretched too thin. Fuel shortages immobilized mechanized units. Battery shortages crippled communications. Even advanced technologies became liabilities when they required constant replenishment. In contrast, systems tied to regenerative processes endured. Field agriculture, improvised water collection, and adaptation to local ecological cycles often sustained forces or civilian populations long after industrial support weakened. The lesson was not romantic, it was practical. Self-renewing systems reduce vulnerability. Plant-generated electricity fits squarely within that pattern. Its output is modest, usually measured in milliwatts, but it is steady. An LED requires very little power. Ultra-low energy sensors require even less. When coupled with capacitors that store small charges, such systems can maintain intermittent transmissions or data logging indefinitely. In survival planning, consistency matters more than peak performance. A constant trickle of power can preserve stored data, maintain timekeeping devices, or operate environmental monitors long after conventional batteries would fail. The distinction between high output and continuous output is honestly critical. Most people focus on wattage, but survival depends on duration. The simplicity of the setup, well, it kind of masks the complexity of the biological work being performed. The physical components of a plant microbial fuel cell are minimal, and a node embedded in oxygen-poor soil near active roots, a cathode exposed to oxygen, a conductive path connecting them. The plant grows normally in its pot. The complexity lies beneath the surface. The rhizosphere, the zone around the roots, is biologically active. Microbes compete, cooperate, adapt, and stabilize in response to nutrient flow. Soil chemistry shifts dynamically. Oxygen gradients form naturally. These processes create conditions suitable for electron transfer without mechanical intervention. Unlike mechanical generators which degrade through friction and where biological systems reorganize, microbial communities adjust to environmental changes. Root systems expand or contract. As long as sunlight and water are available, the energy cycle persists. This resilience parallels broader ecological recovery observed after environmental disruptions in wartime. Landscapes damaged by conflict often regain biological productivity before infrastructure is rebuilt. Living systems, re-establish metabolic cycles without any centralized control. A potted plant is simply a contained ecosystem, demonstrating that principle in miniature. The broader implication here is a redefinition of what energy security really means. In industrial societies, energy security has traditionally meant, protecting centralized infrastructure, power plants, grids, pipelines, and refineries. Disruption at key nodes can cascade rapidly. Biological energy systems operate quite differently. They're decentralized by nature. Each plant, each patch of soil, functions independently. Failure in one location does not compromise the whole. From a strategic standpoint, distributed systems offer a form of resilience that centralized systems simply cannot. They may lack efficiency, but they compensate with redundancy. In survival contexts, this really matters. A single generator represents a single point of failure. but thousands of small biological systems represent distributed capacity. They are harder to eliminate and, honestly, easier to replicate. Plant-generated electricity is not a replacement for large-scale infrastructure. Instead, it's an example of how energy can exist within ecological cycles rather than outside them. The technology remains limited in output, but, significant in concept. Current plant microbial fuel cells cannot power homes or vehicles, and their efficiency remains modest. Still, research continues into electrode materials, soil optimization, and microbial selection to improve performance. But, the historical and strategic importance really lies in the concept rather than the scale. The system demonstrates that electrical generation can in fact be continuous, without combustion, without rotating machinery, and without stored fuel. It can actually be embedded within the same biological processes that produce food and oxygen. For remote sensing, environmental monitoring, and ultra-low power electronics, that kind of continuity is truly valuable. In disaster scenarios where infrastructure collapses, even small, reliable power sources can maintain communication nodes or, preserve data integrity. The lesson here is not technological optimism, it is structural realism. Systems that align with biological cycles inherit biological persistence. What this ultimately reveals about survival is, the importance of integration rather than domination. Modern industrial thinking often treats nature as a resource to be extracted or controlled. Power generation has largely followed that model. Burn fuel, harness, wind, dam rivers. Plant microbial fuel cells, interestingly, invert the approach. They do not force energy production. Instead, they capture what is already occurring as part of metabolic exchange. Historically, survival in extreme conditions has favored those who learn to integrate with local ecological systems rather than override them. Water harvested through condensation, crops adapted to climate shelter, built from local materials. These strategies endure because they align with natural processes. Electrical generation embedded in living soil follows the same principle. A plant in a pot powering an LED may appear insignificant, yet it embodies a deeper shift in perspective. Energy is not solely an industrial achievement. It is a biological constant, waiting to be directed. Understanding that changes how we think about resilience in both war and peace. It reminds us that survival often depends not on scale, but on continuity. If you value in-depth historical analysis that explores overlooked technologies and the strategic lessons behind them, subscribe to Logistics of Survival and share this video with others who take resilience seriously.